right, let's go ahead and get started. Welcome. I have one announcement to make. The first Titan Talk is canceled. I have to keep a promise to Lee. He told me he would only do it if I called it the Titian Talk. So this is not a Titan Talk, this is a Titian Talk. And that's why the beginning of the abstract has the artistic reference. No, but seriously, our first talk today will be by Lee Strubin. I'm not going to tell you too much about. You can read the biography. I'll just add a few things of my own here. One has to do with the fact that's not written in here because I guess Lee is very modest. He's one of the few researchers who's won the Informs Simulation Society. It was called the Timms College on Simulation at the time. Outstanding Publication Award twice. There are a handful that have won it twice. He won it in 1981, which I believe was the very first year it was actually awarded. And then he won it again in 1987. And these were for papers on confidence interval estimation. And there was just one other thing I wanted to add that's not in this. And I know many of Lee's PhD students, they're spread throughout the country in very many prestigious places. And so yesterday I was talking to a group of them. I won't name names because Lee might exact a vengeance on them afterwards. But I asked them for an interesting tidbit to maybe mention in introducing Lee. And the one I got was the following. Lee may be the only rider of a Harley who survived a crash with a Cadillac. And actually the person in the Cadillac, I was told, was the one that got more injured than Lee did. Now, I'm assuming this is true, and then maybe before Lee goes into his technical talk, he can explain that. So please join me in welcoming Lee Strubin from University of California, Berkeley.
There was an accident on a motorcycle. My wife was on the back. I was injured fairly badly, but she was unscathed. She claimed she had an airbag in front of her. I think you'll understand what she means by that as I babble onward here. This is being taped, so I thought perhaps I should have a disclaimer. Corporations, everybody. That's Mitt Romney. It's equal time political. I tried to get something else up there, a quote from Rick Perry. But we're going to talk about art. And I don't want to talk about those people anymore. I want to talk about me. On second thought, you're going to know more about me than either one of us want before this talk's over, so let's talk about you. But first of all, I want to point out the fake logos I have on the top of the screen here. The one on the far upper right is Bayer. They make Alka-Seltzer. So if I upset you during this talk, that's a little product placement, and they'll probably help you out. So I figured that in this audience there are 5 groups, and I'm supposed to talk for an hour, and I thought I would talk for 10 minutes to each of the 5 groups and leave 10 minutes for sort of random rambling. But students are out here. I want to tell students how to get good grades and good recommendations for professors and find out if you want to be an entrepreneur and finally how to get a job. And practitioners, I'd like to give you an idea on how to get an edge on your competition, a little better acceptance of what you're doing and building a little better models. And I know how to do that because I've learned from my mistakes. We've got practitioners, we kind of know that's where the money is. Developers, I would like to talk to you. I've been a software developer. and currently am doing the same thing, but I'd like to give you some ideas on how you might differentiate your product from your competition, and get more acceptance in the classroom at the same time. That's where your future customers are, our students. So we have finally academics. Academics come in lots of flavors, as teachers, as researchers, and as researchers we come as modeling researchers and analysis researchers. And if I finish up, I'd like to talk about how to get almost perfect attendance in class, if you want that. I want to think about whether you like that, and good course evaluations. One year I got the highest evaluations in the university on median, because out of 7, that's what you get. And I figured I wasn't making the course hard enough, so when I get high evaluations, I add content, and low evaluations, I dumb it down a little bit. It seems to work over the years. And then there's the folks who saw this tent and thought it was a revival, and I'm probably going to talk to them more than anyone else here. At least they helped them out. So we'll start with some definitions. System, I think of as a bunch of entities acting for a common purpose. This definition is a little bit different because we define it by the purpose of the system, not by its boundaries or its contents or elements in it, but it's by what it's supposed to do, and that's to get us out of the mind lock of the status quo. We think of a transportation system, a communication system, things like this. It helps us escape that. A noun models using a noun, one system used to study another, is the way I define it. The title of our talk, though, is Models of Verb, and that's using one system to study another. And if you look it up in the dictionary, you see it's a transitive verb. That means it needs a direct object to be active. My thesis advisor's wife was a grammarian. How many people have met a grammarian? So she proofread my thesis. It was bloody, but it wasn't final. I handed in my final thesis hardbound. I did not want her to change anything, because back then, if you changed the second line, you had to retype the whole thesis. So she taught me a little bit of grammar here. But the first thing that's obvious in this talk is the object system is not the model system. They're different, and let's look a little bit on how they're different. I got some email from some colleagues looking at my abstract, and they said I looked maybe slightly negative on animation. I promise I'll use animation in this talk because I found a little button on PowerPoint that said animation. So we take a look at how systems differ from models. First of all, models, we typically have a single objective. Talk about how to maximize this, where certainly in the real world there are multiple objectives. As mentioned this morning, there's a lot of things that's qualitative in the real world. We'll probably code it up and try to make it quantitative, but we run the risk of just because we assign a code doesn't make it quantitative. Example is teaching evaluations. If I give you a 3 out of 7 and I give everybody else a 1, that's a good evaluation. If you give a 3 out of 7, give everybody else a 7, that's a bad evaluation. So my 3 is different than your 3s, but if we average them, we can do standard deviations and all sorts of analysis as if it were quantitative. Dynamic rules. The rules are always changing in the real world. The world's changed when I started that sentence. And static rules, we have to code them in. In some sense, they're static because once we start running them, we typically don't change them. The real world has a large space, probably continuous. We don't know how big M is or how many there are, but we've got to put it on a computer. So we've got a discrete space, it's probably not negative, and there are n things on it. Real systems are open. That means that they influence their environment. The world changes when the system changes. we model things as closed. If we use data for our inputs, that data is old, and we assume that the world won't react or won't change. The input to the simulation won't change when we run it. Adaptive, non-adaptive, that means it changes to its own state. And we don't do that. Real policies are flexible. People change how they do things. They show up late or not. We have to put in code in rigid policies. We fake it with random variables. In the real world, all things are transitive, whereas in the simulation, we are going to have to model things as being resident entities. Typically, our input, we would model things as stationary, independent, and stable, where the real world is dependent, non-stationary, and unstable. So we use IID exponential inputs with, say, a traffic intensity or a rate that is less than 1, or at least traffic intensity less than 1. And I guess the first message I'd like to get from this is when you hear the word exponential, the rest of what you learn will either be obvious or misleading. And if you see IID, that makes it all the worse. The output, we're going to assume is IID normal in some sense, and we can massage the way we run it to make that pretty good. So this is possibly good news, but there's also some other good news about simulation. The real world's unobservable and uncontrollable, whereas our simulation is both. And we can exploit that in how we design our models and how we run our experiments to great advantage. And so we'll talk a little bit about this. Now, most of us out here, or most of the people I meet here, think of themselves as a bit of specialists. They're academics with a discipline. I got in simulation before it was considered a discipline, because I thought discipline's something you do with unruly children. And so it becoming a discipline isn't necessarily a good thing. And specialists, they learn more and more about less and less until they learn everything about nothing. And generalists will learn less and less about more and more until they know nothing about everything. I fancy myself as a bit of a generalist. I was the only one in my high school that was in advanced physics and advanced auto mechanics. I was on the football team and the symphony. I've taken, for credit and grades, 5 languages. I don't speak any of them very well. I didn't take them to learn how to speak them. I really wanted to learn how different groups think. It's not all my fault. My French teacher was German, my Spanish teacher was German, my German teacher was English, and my English teacher was an American. So I did have a Japanese person teaching me Japanese. So why do so many of us specialize? You see people who specialize, they use one simulation language, they focus on that, they go to the same user group year after year. Why do they do that? Well, it's smart. You just look at the math. You know, you're interested in modeling S systems. We'll call those factors. I like to think of the world as experimental design. We've got some factors, and we know M modeling languages or treatments of that. And so we have a chance of making MTS possible mistakes. We learn from our mistakes. So in my experimental design of the world, the unit of learning is the mistake. Of course, in academics, we punish mistakes. I remember from freshman physics only one thing, and that was the question I missed on the exam. I would have done better if I were a worse student. So if we learn from mistakes and we punish mistakes, we punish learning. And I think I have a partial solution to get us out of that. However, as long as we just know one thing, we're okay here. It's going to grow linearly. So the best advice that I can give is to learn 2 things about two different things. This is actually the third best advice I've given my children. The first one is how to make hard decisions. You flip a coin. You've done the analysis. It's a hard decision. You flip a coin. You can only do it once, but once you flip it, you know, because you may want to go 2 out of 3, then you know the answer. The other one is think of the cost of recourse, the price of oops. What if it wasn't what I wanted? What if I made a mistake? How do I undo it? What does it cost me? There's a number of things you can't undo. Having children, joining the military, jumping off a bridge, all those are things that have considerable cost of recourse. This is the third best advice. Learn 2 things about 2 different things. But then you have to do something else, because when you only learn 2 things, you see differences. It takes 3 things to see similarities. And so you decide you must learn a third thing about a second thing, or another thing about a third thing. So we'll have a little bit of art history here. This is a slide. I did actually find out this morning it wasn't called a Titian talk. So we're going to have a little art. This is from a book by Katie Toker. It's the first book ever written about simulation. I have a copy here, and I've read it. It's full of interesting things. This is a simulation of a queuing system where we have 2 different types of customers with different priorities and 1 server. And there's this interesting little item up there. That little pattern is determine what the next event is. The computers were not big enough to have event lists. And so they had to do something else. What you have here is a model that has no events list, and it runs the same speed if he has 10 customers in it or 10 million customers in it. It's just the value of the number that changes. So it doesn't slow down as it gets congested. And some of you have experienced that when your models get congested, they run slower. Well, this one doesn't. So you can learn a little bit, about the things from looking at the past. He also has some comments in these books that are wonderful. For instance, in this model, there's 2 ways of modeling which type of customer arrived. You could generate arrival and then decide after they've arrived which type they are, or you could have 2 separate streams of arrivals. Turns out that the only time those are the same thing is if the inter-arrival time is exponential. Every time I say that word, misleading or obvious. So that, back then we used to use things. I'm trying to simulate a 320 baud modem. I put together the first personal computer at Cornell. It was a Heathkit. You had to put it together yourself. They had 2 modem connections, 320 baud, not kilobaud. That's like A, wait, A, C, wait, backspace. Backspace was wonderful because this is the way we had our input. A punch card doesn't have a backspace key. But of course, you hit the backspace and you got to reboot. So that's one of the things that you do this. It was like a terminal without a monitor. And you had 80 lines. And if you used Fortran, the first 6 of those were numbering the cards, and 5 of those. The 6th one was to tell you whether you wanted more lines. But that was it. That's how you type things. You submitted your cards, and 2 days later, you'd find the first mistake in your program. I always found that 2 minutes later, as I'm walking out of the building, I thought of the first mistake in the program. 2 days later, it was confirmed. We resubmitted it, so we became pretty careful when we did those. Then came along the Selectric. We could actually do some mathematics. We had to take these and put them on with transparent, press things to put the mathematics in your thesis. So imagine your advisor wants another paragraph about them in the first section. You have to type the whole thing. Not only that, you have to put all of the mathematics in by taking this transparency and rubbing it down onto the paper. So, you know, my thesis was 27 pages long. I added a bit of computer printout to make it long enough to bind. But the Selectric came along, and we could do a little bit about that, but not much. And if you bring out the paper by a student or William Seeley Gossett, where he's talking about the probable error of a mean. This is where the t distribution comes from, probably the most influential probability distribution in our society. We make decisions on products and drugs and rules and by using the t distribution. And if you read Gossett's paper, and it's on Wikipedia, you'll see some notation that is from a Selectric because it has subscripts. But what this notation here means is this is the sum of xij and xik, where xi1, 1 through n, and I not equal to j. So we didn't have a sigma at that point. Some of you might know that that's, if you know me a little bit, that's probably was a good time in my life, pre-sigma. Okay, so if you have a problem, this is my most important piece of computer equipment. I find that if you work for an hour, it goes off. This is not mine. Mine is broken. I've thrown it against the wall a number of times, and it's been taped together a number of times. But when it goes off, you take a walk. Pretend you've submitted your deck of cards to the computer, and 2 days later, it's going to tell you what you did wrong. You walk out the door, and you realize what you've done wrong. So talking about modeling, the verb of modeling, I look at 13 textbooks, IEOR textbooks, and what are the steps in modeling that I find? And I find that all 13 of them thought we should formulate the problem. One thought we should establish a system boundary. One thought we should factor the problem. What's our objective? What are our constraints? One thought we should state our prejudice, and I was trained by Bayesians. That didn't seem right. They all eventually somewhere equated modeling to seeking an analogy, but in the steps, only 2 of the 13 thought you should actually do it. Level of detail, not there. Define some symbols. These are all mathematical models. So if you don't define those symbols, it's a little hard to understand. State the obvious, update the model, choose a technique. 3 out of the 13 thought we should collect some data, but only 2 of the 13 thought we should do anything with it. Everybody said, build the model, perform the analysis, but less than half of them thought we should test our solution, and half of those thought we should do anything with our solution. So how do we model? Now, I've dimmed this out. These are copied from a couple of simulation textbooks on how we model, and to protect me from a lawsuit, I dim them out so you can't quite read them, but they all pretty much say the same thing, that you collect data, you code your model, and then there's a directional arrow to experiment with that model, and then you implement the results. It's not the way that I've done it. I have another one's kind of my favorite. This is, again, a process that has a start and a finish, but it has a whole lot of other stuff that's just great. Tells you to stop, stop again, stop, stop, stop. Stop doing this. And so this is the outline for my course. It's not linear. It's how I've done simulations. You start by thinking, do you have enough time, energy, and money? I consider those the 3 basic elements of life. When you're young, you have lots of time and energy, and if you spend them wisely when you're old, you have a little bit of money to hire young people to do things that would take time and energy. But you can typically spend some energy and to get some money, spend some time to get some money, spend some money to save some time. So but you want to keep them in balance. If they get out of balance, then you need to think again. Once you've got the resources to do this little loop up here is one that I don't see happening very often, and that's to anticipate the human behavior. The reason you're doing your simulation is because there's some uncertainty on what people should do. Typically, there's people think we should do one thing, and there's a bunch of folks think we ought to do the other. So you want to find out what they are. You formulate the questions, but then you mock up some answers. What do the answers look like? And typically when I do that, they say, no, that's not what I mean. I would like a chart, or that's a number. I didn't mean that. One of the clients I had in consulting was working on a call center. They wanted to improve customer service. I said, why do you want to do that? Says, well, so we have more customers. And well, why do you want to do that? So we'll make more money. And I finally believed them on that, except that it turned out they weren't really trying to design the call center as much as do market segmenting. They wanted customers who were profitable to get good service and customers who were not profitable to not get so good service. And that was the basic question that they wanted to do. How should we do that? And that's a very different question than improving customer service. Identify your prejudices in there. Most of your clients have a preconceived notion of what's going to happen. Then you design some experiments. Now, I haven't collected any data, haven't thought about what the system should do. So I go down here, and still while we're in the upper loop, we're doing them all together, we replan our study, resecure our resources, develop a model. We recode until we have no known errors. That's the best you're ever going to do with a program, is no known errors. And when you know one, you fix it, and then you're in the no known error state. Do some sensitivity analysis, design some experiments, and if necessary, collect some data, because now you know what data you'll need. Philip Kiviat, who gave the first Titian speech, he said one of the biggest reasons for the failure of a simulation study is lack of data. I don't think that's reasonable. I think data is something that you will use, but it's dated, it's old, well, don't get me started about data. So what we do is analyze, advise, we caution, we adjust expectations, get a little more money, a little more time, and continue the loop, keep thinking, and go through that. So this process is quite different than the ones that you see in the textbook. There is no end. It's a continuous loop, many continuous loops happening simultaneously. So we're going to talk about next languages, and I don't mean software when I say languages. I mean the way that we get the illusion that we understand the system and how we view it. And most people that do discrete event simulations here use this entity flow, process flow, job-driven kind of paradigm, or activity cycles, systems dynamics, agent-based modeling, event relationship graphs, generalized semi-Markov processes, stochastic time Petri nets, and my current activities are involved in agent-based analysis, which comes out of the same kinds of structure as agent-based modeling. I'll talk a bit about that because I like to talk about that. And then combining some of the notions of generalized semi-Markov processes, event graphs, and stochastic Petri nets into a way of viewing systems. A little more history. The first process flow language was GPSS, and it was built in blocks that were triggered by these transient entities that were generated in the beginning. They would join a queue, that's Q1. If they could seize or be seized by a resource, which was called a facility. This is originally to model computer systems or storage, depending on whether it's single or multiple resource. But they would seize it, and then they would depart the queue. So the little symbols out to the side of the blocks were matched. You join Q1, you depart Q1. And it was used to collect data. You're seized by resource 1 or seize it. You go through this advanced block, and that's where time passes. During the advanced block, the entity waits in there, puts something on the future events chain that will happen when we get to it. When we get to it, we release the server we seized and terminate, that is, free that record space. This has been, it's been condensed and then recondensed. And as you're doing this and renamed, not for everything. This is an example of line balancing where we have 100, dividing a job into 100 subtasks. We want to see if it's 99 subtasks, we build another model. So there's other ways of doing it. Petri nets, just so we know what we're talking about, there are two types of vertices or nodes in a graph. Places, which are circles, transitions are bars. You have a time. You mark the places with tokens, and when you have a token in each of the input, a timer starts, and when all the outputs, when the timer goes off, takes one of the tokens from the input to the output, and you have thin bars for 0 conditions, 0 times. That's very important, useful. Lots of enrichments. Petri nets are not Turing complete. You have in their raw form. So you enrich them. This is our single server queue with 2 types of jobs. We've got pending arrivals in this place. That's the count of the tokens. They're different colors because they might be different types. The queue's empty. We've got 2 idle servers and 3 busy servers and random firing times. You can take a Petri net that is a stochastic Petri net that I just showed you and condense it using colored tokens. There's a wonderful book by Peter Haas on this. The nice thing about Petri nets is you don't have to know where the token came from. So they don't necessarily have to be connected. They can be isolated. And so this allows us to build models without hooking them all together for our user. And this is an example from 1990 where these 4 little Petri nets were done by people on a shop floor, I believe at Mitsubishi Electronics, and they hooked together and build simulation of what they're doing. Event relationship graphs. This is all you need to know. It's Turing complete. You've got an event, it changes the state. If there's a condition, then there will perhaps be another event scheduled after delay of time t. A little bit more notation, you might want to wait until the thing's true. Here's our single server queue. Pretty simple state changes. When they enter, the queue goes up. When they start service, the queue goes down. There's 1 less idle server. When they leave, there's 1 more idle server. You read these by reading each edge. In less than 1 sentence per edge, you can capture all of the dynamics. First edge says, jobs enter the system at random intervals. You start service if you find an idle server. They leave after being served. If there's still jobs in line, you'll start the next job. So you have this complete description of the system in English that has the event names in it. So you read them that way. This is an example that I'll use in a second about if you have a fixed number of resources, then queues the total of jobs. This is like Toker's model. If queue's 10 or 10 million, it runs the same speed. So we can convert these into process flows by just simply hiding some things. So we look at this entity flow process where we're taking this job and dividing it into 100 tasks. That would look like this. The job enters in Q1 and it stays in Qi, and you just go to the next one if you haven't gotten to all of them. All you have to do to change this model from 100 to 99 is change the value of m, which you can do while it's running. In fact, you can run several values of m at the same time. And at that point, all values of m at the same time. Your experiment is your model. You run the experiment. You can change the time scales at each of these values. If it's not doing very well, don't simulate it very much. Pretty soon you're simulating only the right answer. It's an idea called time dilation. This is an event graph of a automatic material handling system in a semiconductor fab. But this isn't for everyone. Because, back to art, this is an actual event graph of the Joint Genome Lab Institute in Livermore, California. It's a model they've been using for years. I had them autograph it. I figured this would be worth something. But this is art. This would be a very simple system to model using process flow. So what we've been trying to do lately is to take some notions from generalized semi-Markov processes, from Petri nets, and from event graphs, and develop something that we're currently calling activity interaction, but these are things that can be created by themselves, not hooked together. One of the things we've done is color the places, if that means anything to you, but this is what you need to start, what you need to finish, and then each activity has its own clock that may run at a state-dependent rate, like a generalized semi-Markov process. It's been used in some pharmaceutical companies. I became an entrepreneur October 2007, right when the crash occurred. A couple of my graduate students who were my teaching assistants said, well, should we teach them this way of building models? They said, well, let's see how it works. They said, no, well, let's don't teach them, let's form a company. So one of them dropped out of school, the other one finished his PhD, they formed a company, it's grown organically. First job, they saved their client $20 million. They've saved several $100 million of their client's money since then, and they're able to simulate between 1 and 2 years of a manufacturing a biopharmaceutical plant in 1 second on a personal computer. And that means all the way down to the cleaning equipment, because these activities are occurring in parallel. They do use the cloud to do this, but it has to do with how you model. Very interesting facility. I mean, you've got a facility in Berkeley. It's 32 acres. These are the employees, and what they're holding up is the annual production. This is a life-saving drug. It's mainly for children. If you don't get it, you die, and that's all they make in a year. So if you double the powder, you'll save lots of lives. Very interesting place. This is the look of an activity interaction model of a biopharmaceutical. There was no arrows connected. Those arrows there are artificial to show product flow. But each one of these activities are created independently of the other. They're not hooked together. The computer does the following. It says, well, what do I need resources do I need for these activities? And then what other activities do these resources do? And then we look at these activities. Again, this would be very hard to program this network. So it's not done. It's done automatically. Right now we're at the emergency department in UC Davis. They have 6 emergency rooms, and what they've done is RFID'd all the equipment the nurses carry around. These are actually phones that we're using with an Android tracker, and when we see a number of these resources together with a patient, we think, well, there's an activity going along. The medical record has asked for a procedure, the doctor's order procedure. We see it happening because you have a sonographer and a sonograph and a patient, they're probably getting a sonogram together. But that's confirmed later by the medical record when they enter it. And so this system starts out as a process flow, kind of emergency room, like most of them, but it learns from the data system new activities, new events to do it. The last thing I'm going to talk about is, in 1 minute, agent-based analysis. This is the scatter diagram. You look at the scatter diagram, connect the dots, it tells you something different. You can take, this is I'm trying my YouTube video, which I downloaded, of agents flying around. And the idea here is that some of those agents in this flock can be the output of real simulations, and they're scripted, and we want to replicate them, but it's very expensive to get the real ones. We just create a flock of agents that fly with them, and they, depending a little bit on what kind of variability we want, we see how close they are to each other. This has been used in a number of ways. We have a talk about it. One that's quite interesting is fishing in Iceland. They have different kinds of fish and different kinds of quota on different kinds of fish. And you can see on the lower left that cod is regulated. The catch of cod is regulated. The catch of haddock is not. However, the populations, which is the upper two things, tend to fluctuate similarly. This is one of the fish they eat in Iceland called a lumpfish. And if you're not upset stomach yet, a little more plug for bear. So closing, one of the experiments I was given, they had 32 factors. They wanted to try high and low of all of them. It took 20 minutes each. That simulation would take 160,000 years to do one replicate. We've got to do something else, and we can try to do time dilation, meta-replication, make the model of the experiment on the cloud. Those things seem to work. So learn two different things about two different things. Students, practitioners, developers, academics, I have things that probably can help or offend, but let me just close here the way I opened with a plug for Bayer Alka-Seltzer and a thank you. Oh, no. Any questions? I don't. Okay. Let me prompt some a little bit by looking at the audience. Maybe from the students, there might be some questions on how to get good grades, good recommendations. You do them the same way. You never cut class, you sit in the front row, and you pretend to be interested. Works. Go to office hours. I've had people call me up in graduate school and say, you give this kid a great recommendation, you got a D in your class. And I said, but they seem so interested. Should you become an entrepreneur? Buy some chickens. If you still think you might want to be an entrepreneur, buy more chickens. And then when you decide to become an entrepreneur, make sure that you have a partner to feed the chickens. The entrepreneurs here know what I mean. How to get a job? Don't do a term project, do a term product and put it on YouTube. That's what my students have been doing for the last couple of years, and they send the link to employers, and with a product, it's more generic. It's more about a problem. If you do a specific, the coffee shop down the street, they don't care that much. So do that. Attend 3 software user groups so you can see the similarities and the differences, and learn about event graphs. Practitioners, keep a perspective on data. It's data. It should be called data because it's dated. It's distorted. You want demand, you get orders because some people, they might not wait. Time between failures, it includes the repair time. Data can be deleted. You've got censored data. You've got data can be damaged, data entry errors, observer errors. It can be dependent or stationary. They're different. Dependent means people don't like to join long lines. Stationary means Friday is not like Tuesday. It's devaluing and demeaning. You look at a doctor consult, it becomes a diagnostic code and a time. There's more there. It's doctored, well-intentioned people try to clean it up, and it's perhaps deceptive. It's not so well-intentioned. So, advice, attend 3 software user groups, not the same one that you've attended all along, and learn about event graphs. Software developers, I think that if you look at the research, there's lots of great ideas out there that could differentiate your product. Plus, if you're using a professor's idea, he'll want his class to see that software, and so he'll use the software, or she'll use the software in the class, and that's your future customers. So it works well for you. Don't claim to be the best tool for all problems. It's not. Provide hooks for collaborative development, and if you can, at least give them the source code for their model, and learn about event graphs. Same thing, attend 3 different software user groups, maybe your own, they'll miss you. And in case I didn't mention it, learn about event graphs. Academics, you want near perfect attendance? You may not. But the way it works is you give advanced placement exams in class. They add that to the next exam score. I have students calling up because they missed class. They said, can we take it again? People beg for advanced placement. These are quizzes, pop quizzes. I called them pop quizzes nobody liked. At advanced placement, they love it. Good teaching evaluations, do them on the Tuesday of Thanksgiving week. Only the students who care will be there. It's worked. Assigned term products, not projects, so people can look at a generic problem, not a specific problem, and see a little bit about what's going on there. Plus, they can say, don't punish failure. Partial solution to that is that once the course is over, I let the students vote on the weighting of the exams and the product. They can go high or low, 10 or 30% on each one. Now, I give everybody every weighting because I want to be fair, but I let them vote just so they think they have some input. This is being taped, isn't it? Oh, how quaint. Taped. What does that mean? It's being recorded. They're not putting it on tape. Okay. But if you go ahead and let them vote on this, then they don't have to do everything right to get an A. They can make a mistake and still get an A because they decide they don't want to weight their mistake. Make modeling and analysis researchers. I have a paper in the modeling track and a paper in the analysis track, and I don't see the same people in those groups. And I think that you probably should. Don't teach only one simulation language. If you must teach a language-based course, change languages periodically. I've done that quite a bit. Insist you get your model source code for your students. That is not the source code for the software. You're not going to get that, but when they've created a model, it'd be nice if they had that code. So attend 3 different software groups, and yes, learn about event graphs. So there I am, and you know the next thing. Thank you.
We still have time for questions, so if there are any questions. Okay, the question is, what is the goal of the education system?
Well, now, if I were elected president, I'd close 3 departments. I can't get any of them. The goal of the education system. I know what my goal is the students are not afraid to make mistakes, and they learn more art. You know, science, art, and technology are all part of our class. And as the technology's grown, they've taken more of the time away from the science and art. I've decided that I want to keep the art there, so the science, they can read about it. But it's a balancing act. The goal of education, I know what my goal is. I want my students to think critically. I want them to ask questions. If they know the right questions, then I think that's the bet. One year I gave a reverse exam where the students write the questions, not the answers. And then I would try to answer them. But we grade the questions. So I'm trying everything. I even had a 1,000,000-point exam one year so they wouldn't complain so much. I'd say, yeah, I'll give you another 1,000 points. They would walk away happy for a few seconds. But, sorry. Any other questions? Yeah, oh, Russell. Sorry, Susan. I'm not. What do I expect people to use instead of data? I don't expect them not to use data, but I expect them to remember it is data. It's about the past, and if you're lucky, it's about the present, but it's not about the future. And so you have to ask your question, how much do you think the future is going to be like the past? How much has it been like the past? Not too much. So I think you don't want to use it for the future. Yes. Susan. Teaching the art aspect, typically showing these various paradigms, ways of thinking, and they develop their own, encourage them to develop their own way of doing it. And some people can do different things. I show them how I do it, and I do it different times. But how do you teach the art of modeling? Well, I've taken courses in watercolors and things like this, and I've learned a lot. I know it's not the green crown for the tree. There are different colors there. So you learn art, and then you develop your own. You look back and you see that Da Vinci made his own paint. He had to know chemistry, he had to know all those things. And I think that our technology, we don't do that, and that's keeping us away. So there's a conflict there. Minimize the technology is the best I can do. Anything else? Thought I used up all the time. Good. We did. Fine. Okay.
Okay, if you have any further questions, you can come up to Lee. I'm sure he'll be willing to answer them one-on-one. But thank you very much, Lee, and everyone, please be sure to come tomorrow to tomorrow's Titan Talk, which I'm sure will be just as interesting and provocative. Thank you.